So in the previous video, we talked about chemical equilibrium and how reactions, when they're reversible, they generally tend to get to a state where they're at equilibrium. All right, but once that equilibrium is reached, it doesn't necessarily mean that it has to stay at equilibrium permanently. You can do things to disrupt that equilibrium, and whenever an equilibrium is disrupted, and there's several ways that you can disrupt it, essentially what's going to happen is that things are going to want to get back to that equilibrium position. All right, and this concept is called LeChatlier's principle. And essentially what this says is that if the chemical equilibrium is disrupted for any reason, the reaction will tend to respond in a way to restore that equilibrium. All right, and there's several ways that the equilibrium can be disrupted. We're going to talk about a couple different ways that this can occur. The first method way that can happen is the addition of reactants or products. All right. All right. So this is probably the simplest way to understand LeChatlier's principle. So let's say that we've got this reversible reaction. A plus B can make C. All right, and this can go either way, and we've defined these rate constants here. All right, so at equilibrium, we know we're just going to say that the concentration of C is 2, A is 4, and B is 2. All right, we can assume that the units are molar, but it doesn't matter here. So we can show an equilibrium expression. We'll put the C up top. We put A and B on bottom. We don't need to worry about squaring anything because all the coefficients are 1. And we're just going to take our values, plug them in, and we get that the KEQ is going to equal 0.25. All right. So what would happen? So this would be, picture this right here being our reaction at equilibrium. And we're going to assume that these are solute particles dissolved in solution. All right, so picture these as just being like ions or just molecules dissolved in water. All right, so if this thing were was to be at equilibrium and we just let it be, all right, it would tend to just stay at equilibrium. And it doesn't mean that the reaction has stopped. Again, it just means that that the rate of this reaction is equal to the rate of this reaction, so these concentrations would tend to stay stable over time. All right, but what would happen if we were to just add, if we had a bottle of just pure C laying around, and we just were to add some of that material to this reaction mixture? All right, so at the moment right after the addition, all right, notice you're going to have a couple of extra of these C's around. All right, you had 2 C's over here, and now you've got 2 extra C's. All right, well, the problem is we can calculate a Q value at this particular moment. All right, so at that, we'll just assume that this thing right here is 1 liter. All right, so that if you add 2 moles of C, you're increasing the molarity by that much. All right, so if we calculate what that new Q value is, notice that the concentration of C has gone from 2 to 4. All right, and if we calculate what that would correspond to, we would find that its value is 0.5. All right, and so what this means is that this reaction right here, assuming everything else about it has stayed the same, would not be at equilibrium anymore. And that's because your Q value, which is 0.5, does not equal your equilibrium value. All right, so think of your equilibrium value as the value that that Q wants to be at when it's at equilibrium. It's the state where the reaction is, essentially you can think of it as the state where the reaction is happy. So how is this going to affect the reaction if this were to happen? All right, well, let's to see how that would affect things, let's go back and just consider the moment right after the addition of C. All right, well, we still have in this reaction, we have, remember, all your equilibrium is the interaction between the forward rate and the and the reverse rate. All right, so we would still have a forward rate law. All right, and we would still have a reverse rate law. All right, so ask yourself, what would change if we were to have added some C to the reaction when it was at equilibrium? All right, well, notice that what that does is right after you add some C, that's going to increase the concentration of your C. All right, so at that point in time, you still have the same concentrations of A and B. All right, so the forward rate would not be affected. All right, you still have the same concentrations of A and B. You still have the same rate constant, so your forward rate is still the same. But if you look at the reverse rate, the rate of this thing going backwards, all right, well, your rate constant is the same, but you now have a higher concentration of C. So if you multiply this higher concentration of C times a constant, your overall reverse rate is increased relative to when it was at equilibrium. All right. So if you let a little bit of time pass, what's going to happen? All right. Well, if you allow this situation to go for a little while, while you have a relatively higher reverse rate compared to forward rate, well, what that's going to do is it's going to tend to drop the concentration of C, because disproportionately more of the C is going to A and B than the other way around. All right, so C is going to tend to go down after a little bit of time passes, but since the reverse rate is higher, that's going to, whenever C reacts, it's going to increase the amount of A and B. All right, so A and B is going to start to get higher. All right, so compared to this moment before, we now have higher A and B, and we have lower C. All right, so therefore, your forward rate is going to start to pick back up. All right, and your reverse rate is going to start to slow down. All right, so again, at the very beginning, after you met at C, your reverse rate is going to be much greater than the forward rate, but eventually it's going to just be slightly higher. And as time goes on, the reverse rate is going to keep on slowing down. The forward rate is going to keep on speeding up until eventually that reverse rate is going to equal the forward rate. And at that point, your reaction would be back at equilibrium. All right, so that's the classic example of LeChatlier's principle. All right, and again, it's not the principle. It's not magic. It's just a simple application of looking at what you would expect to happen if you had if you just looked at these different rates, the forward rate and the reverse rate. Okay, in the previous example, we investigated what would happen if you added some reactants or products. All right, and that what happened is that it just affected the concentrations of things in your reaction, and your reaction would respond to that. All right. Well, a similar type of thing could happen if you removed products or reactants. All right. So, for example, we could say in this situation, what would happen if instead of C going up from 2 to 4, what would happen if it went down from 2 to 1? All right. Well, we could go through the same mental exercise. Well, if you now had a lower rate of C, that would decrease the reverse rate, and we could go through all of that. And I think that you should be able to go through that exercise. But what I want to focus on here is to talk about what are the kinds of situations where this could happen. All right, because if you were to say, how could I increase the amount of a product or reactant? Well, that's fairly easy. If you've got any of these things and you've got a bottle of it laying around, which is just pure C or pure A or pure B, you just add some of that material to your reaction mixture. All right, but removing things is not that simple. All right, at first you might think, well, if I've got a solution where I've got all these things dissolved in it, well, how do I just get A out of there? I can't just reach in there and pluck molecules of A out of the reaction mixture. So how would that ever happen where you've got a situation where products and reactants are being removed? All right, so there's two common situations where you would run into this. All right, the first situation would be if you had a product which is a gas. All right, so consider this equilibrium right here. We've got carbonic acid, which is aqueous. All right, and the thing about carbonic acid is it can undergo. This is a chemical that very readily decomposes to make water and carbon dioxide. All right, but this reaction right here is an equilibrium reaction. All right, So it can decompose to make water and carbon dioxide, but water and carbon dioxide can combine to make carbonic acid. All right. So what's the type of situation where this reaction right here would reach equilibrium? All right. Well, the only way that you're going to get this reaction to be at equilibrium would be at a situation, I'm going to zoom in right here, all right, would be at a situation like this. And essentially this is just like seltzer water, all right? You've got a bottle. I made my bottle really wide so I could show the equation right there. But imagine this is just like a bottle of seltzer water, which is kind of like club soda, and it's capped, all right? Well, the reason it needs to be capped is if you've got carbon dioxide, well, if it's uncapped, all that carbon dioxide can just, become undissolved and bubble out, and it eventually leaves the vessel. All right, but since it's capped, all that carbon dioxide gets trapped there, and you're gonna what that causes is there to be a certain amount of dissolved carbon dioxide in that liquid. All right, and so that carbon dioxide can react with water, and that can make some carbonic acid, but the reaction can also go to the right. And since that you've got a situation where you've trapped that carbon dioxide, this right here eventually will reach equilibrium. All right, so classic example of a way something could be removed. Well, ask yourself, what would happen if we were to take the top off here? Well, if you take the top off there, or you uncap it, all that carbon dioxide is going to come rushing out of the container. It's not going to be under pressure anymore. And what that's going to allow to happen is that some of this undissolved carbon dioxide, some of this dissolved carbon dioxide is going to now be able to become gas carbon dioxide in the space above the liquid. All right, and eventually that's going to leave. All right, so essentially all that dissolved carbon dioxide, which was required for this equilibrium to exist, is now free to leave. All right, so essentially this is a classic example of how a product, one of these things, is going to be removed from the equilibrium. All right, it's not happening because you're literally reaching in there and plucking out carbon dioxide. It's just that it comes, just like the bubbles in soda, it becomes undissolved, becomes part of the air, and it just floats away. So it's not in the solution to be part of the equilibrium anymore. All right, so what that's going to cause is if you remove some of the product, that's going to shift the reaction to the right. All right, and a way that you represent that is the reaction that becomes favored. You show that with a longer arrow. The reaction which is disfavored, you show with a reverse arrow. All right, so whenever you do this, notice that you're essentially going to always have a tremendously low concentration of CO2 because it's going to be constantly leaving. So it can never build up in the aqueous solution. Therefore, this reaction would never reach equilibrium. It's just going to continue going to the right. And once it makes some of the CO2, it bubbles out, and so it continues going to the right. It's trying to get back to that equilibrium, but it can never get there. All right. So another example is going to be if you had a solid product. Okay, so let's pretend that we had this equilibrium and we had this chemical D as a product. And one thing that we know about D is that it's very soluble at higher temperatures, but it's not so soluble at lower temperatures. All right, well, if we just take a look at this reaction right here, we could write a KEQ expression. And at higher temperatures, notice, since at higher temperatures you can get a decent amount of that dissolved, this could be relatively high, and you could reach an equilibrium state. But what would happen if we were to take this and we were to cool it down? Well, if we cool this down and some of that dissolved D starts becoming undissolved D, all right, it just forms a solid, and the solid, let's say, just sinks to the bottom of the solution. All right, well, essentially what that's going to cause is that your concentration of D is going to go down, because remember, this is concentration of dissolved D. All right, so if that isn't soluble, then this concentration right here goes down. That's going to force this reaction to move to the right. All right, essentially what's happening is that the reaction is trying to get back to this equilibrium level of concentrations, but it can't do it because as soon as D gets formed, it falls out of solution and it's no longer part of this right here. So it keeps on going to the right.